Hello, I'm Shomadeep and I'll be presenting our paper titled Language Models are Crossword Solvers. In this paper, we study constrained language generation with large language models, which is a pressing challenge in many NLP applications. In particular, we analyze crossword puzzles, which are a great example of a constrained language generation task. Our main goal with this paper is not to create specialized crossword solving systems, but rather to identify strengths and, more importantly, deficiencies demonstrated by LLMs in this regard. So, what are crosswords? They are a kind of word puzzle played on a 15 by 15 grid of white and black squares, some of which are tagged with numbers. Corresponding to these numbers, we have clues which provide hints regarding the answer to be placed at a certain grid location. Additionally, the number of allocated squares for a particular answer limits the length of allowable answers, and squares with overlaps, for example the ones highlighted in gray, limit the allowable characters. As an example, consider square number 2, where the first letter of the answer to clue 2 down must be the same as the second letter to the answer to clue 1 across. There are several variants of crosswords, and in this paper we analyze straight and cryptic crosswords. The American style or straight crosswords, like the ones you would find in the New York Times puzzle section, have relatively simpler clues that involve synonyms, word knowledge, etc., but feature denser grids. The UK style or cryptic crosswords feature more involved clues, and solving them requires a plethora of relevant skills ranging from arithmetics and reasoning to knowledge about homophones and celebrity trivia. Let's look at a few experiments in this regard, and in particular, we analyze the adeptness of foundational LLMs at this multifaceted task. Following in the footsteps of previous efforts in this area, we first analyze crossword solving as a QA task. That is, we provide the LLM with the clue and expected length of the answer and ask it to produce the answer. We observe that the performance of LLMs in this regard improves with scale, and some models significantly improve upon previously reported results. The performance of the models are much better on straight crosswords, which is not surprising given that cryptics feature much more complex clues. However, this is not how humans solve crosswords, and this approach completely ignores the grid structure imposed by crosswords. Some clues will be harder than others, but the answer from a particular clue can also reveal crucial information regarding other clues. So the next question we ask is, can LLMs effectively leverage this revealed information to improve? Turns out the answer is yes. In this experiment, we provide the language model with letter masks indicating revealed characters and see if their performance improves. An example query would be drink of spirits getting us fired, where drink of spirits can mean a shot and fired can also mean shot, which is the ground truth answer. In this example, we reveal 50% of characters with the letter mask -H-T. The table shows that performance improves with an increase in the percentage of revealed characters in almost all cases, thus indicating that LLMs can exploit this information to improve clue answering performance. This is a crucial skill required to solve full crosswords. Since we observed massive performance improvements in some LLMs, we are naturally led to the question, is this because of contamination? That is, have the models already seen most of these crossword clues and solutions during training? To ascertain if this is the case, we collected a post-cutoff dataset that only contains clues published after the knowledge cutoff date of all LLMs in consideration and from the same source. This dataset has also been cross-referenced against a large database of old crossword answers to ensure there are no duplicates. We find no appreciable difference in performance, leading us to conclude that these models have the ability to generalize beyond potential contamination. We also tested the reasoning abilities of these models in this regard. A thought chain corresponding to a clue was generated with a three-shot chain of thought prompt, which was then evaluated for logical soundness and factual accuracy. Turns out 74% of correct answers are accompanied by sound explanations for the solution. The next aspect we wish to address is solving full crosswords. We introduce a novel LLM guided search strategy called sweep clip to solve crosswords with foundational LLMs. Our algorithm first generates candidate answers corresponding to every clue in a step we call sweep, and then prune this set of answers based on certain graph-based criteria, which is called clip. This process repeats until the whole crossword is solved or the LLM computational budget is exhausted. We prune answers by first selecting the largest connected component to ensure that a large number of answers are somewhat coherent amongst themselves, and further prune any potential conflicting answers. In subsequent steps, we generate candidate answers in the neighborhood of existing answers, followed by the same pruning strategy. Our algorithm, alongside GPT-4 Turbo, manages to solve 48% of crosswords without any errors and half fills 98% of crosswords. The final character level accuracy is 93.1% and the final clue level accuracy is 89.6%. Note that the baseline accuracy, that is, the accuracy without employing our algorithm, is 43.5%. The performance with Llama 3 70 billion is worse, but a significant uplift in clue answering accuracy is still observed. The final aspect we analyze is length adherence or counting, and it's not all roses and sunshines in this department. In particular, we are interested in an LLM's ability to count the number of constituent characters making up a word or phrase, which is a crucial ability for solving crosswords and many other tasks. We find that LLMs generate answers of the wrong length 16% of the time on the New York Times dataset and 26% of the time on a cryptic dataset in the best case scenario. Having observed this trend, we probed the general counting abilities demonstrated by LLMs and found that their counting performance drops with prevalence of a word. That is, their ability to count the constituent characters in a word correlates with the unigram frequency of the word, leading us to hypothesize that this ability is learned from some dataset specific artifact. There is also a significant drop in counting performance between words that are part of the model vocabulary and randomly generated gibberish following the same length distribution. The bulk of evidence points to the fact that these LLMs do not have a generalizable ability to perform subtoken counting. This is a major hindrance for crossword solving too, and even when the answer generated by the LLMs is semantically close, for example, lecturer versus professor, 46% of the time the answer is wrong owing to a length mismatch. Thus, in this paper, we have analyzed several aspects of this constrained language generation task and found that LLMs demonstrate some desirable qualities in this regard. In particular, their ability to grasp the semantics of the clue is commendable, and the fact that they can exploit hints to improve performance is rather serendipitous. We also use this property to demonstrate full crossword solving with foundational LLMs. Counting, however, still remains a challenge, and further research in this area would be compelling. If you would like to reach out with your questions or comments, feel free to contact me using the QR code below, and further details are available in our manuscript. Thank you for listening.